Hello, everyone. This is our class number 20. We're going to go over the theory of bagging and random forest in machine learning. So after you know what is the idea behind decision trees in general, then understanding the random forest and bagging is going to be very simple and neat, right? The idea is that instead of working with one tree, why not take advantage of wisdom of the crowd, right? So let's combine multiple weak learners and make a consensus prediction, right? For example, the idea is that let's make multiple trees out of the data set, right? And these trees are going to be randomly drawn from the entire data set. And then depending on the question, if it is a classification problem, we're going to come up with different classes, right? So for example, tree number one is going to give you one prediction. So this is class number one, tree number two, class number two, tree number three, and then this is capital letter B. We're going to talk about it. This is a number of bootstrap that we use in the random forest. Let's say we have class B, right? If it is classification. And then the output is going to be the majority vote, right? So the class of the output is going to be, for example, if class one, we're talking about loans, right? So default versus not default. If tree says that if the first decision tree says that this is a default, second decision tree says that this is a default, and maybe the last one says that this is a non-default. So the consensus is going to be default because the majority of the trees predicted that the output is going to be default. The same story goes with the random forest regression models, right? So for example, the outputs are going to be, so the output of the tree number one is going to be one number. Let's call it y hat one. The output of the tree number two, y hat two, and etc., right? So the output of the entire model is going to be the average of all these outputs, right? So average of all these y hat j's, right? So the idea is very simple, and the goal is to increase the accuracy of the simple decision trees by taking advantage of the wisdom of the crowd. Okay. Now let's go over the roadmap, and again, we're continuing our journey in tree-based models. Last class we covered decision trees, and now today we're going to improve the decision trees by the bootstrap aggregation. So you will see that bagging and random forest in general, when it comes to accuracy, they're going to outperform the decision trees. And next class, we're going to even improve it more. So we're going to use boosting. So today we're going to talk about the idea of what is bagging and what is boosting, and basically what are ensemble methods in general. So the topics that we cover is going to be the first one. Part one is going to be our motivation, and talk about the ensemble learning. In part two, we'll look what's behind the bootstrap aggregation and random forest algorithms. In part three, we will talk about hyperparameters, and we will also look at what do we mean by feature importance in random forest and bagging. And finally, in part four, we're going to talk about the pros and cons and conclude the class with applications in finance, applications of bagging and random forest in finance. Okay, so let's start with first part. Why not a simple tree? So remember, the goal is to reduce the bias and variance at the same time, right? And the idea is that can we push the total error down even further? So from our last class, if you remember, we talked about decision trees. We said that, okay, let's start with the very bushy tree. So it was our initial tree. Let's call it decision tree one. Start with a very bushy tree because the bias is going to be small, but unfortunately, this very bushy tree is going to overfit, right, in the train set, and then it's going to perform very poorly in the test set because it is overfitting. We said, okay, what's the solution? The solution is that what if we prune it back? We start with a very bushy tree and then we prune it back. So maybe we get to the trade-off between bias and variance. The hope is that by cutting out some branches, the bias is going to increase a little bit. If you look at the bias is going to increase a little bit, but on the other hand, the variance is going to decrease a lot. And the hope is that eventually we get to the optimal value for the number of terminal nodes in the model, right? So remember, the model complexity in decision trees are the number of terminal nodes. We can think of non-terminal nodes as a model complexity. Yeah, so let's call it decision tree optimized, right? So this was the idea of decision trees, right? So we started with the bushy tree, we prune it back to get a better outcomes. But what is the idea of bagging and random forest in general? So in bagging, the focus is on reducing the variance part, right? So we are going to say that, is there a way that we can, let me just erase this extra stuff. Is there a way that we can push this variance curve, the entire variance curve down? This is the idea of random forest, right? Or bagging in general. And so if we can do that, so we say that bagging focuses on reducing the variance, the model variance, right? By doing that, we will be able to reduce the entire error. If it is error in the test set, right? If it is classification, let's say we want to increase the accuracy or reduce the error rate. If it is regression, we want to reduce the mean squared error or RSS. Okay. So that's the idea of bagging, and we're going to look at the mechanism of how bagging is able to do that. And for boosting, however, the goal is to reduce the bias. So in boosting, we will start with a very small tree. Actually, we're going to combine lots of small trees together. And the idea is that the variance is already small. And let's see if we can reduce this bias, the entire curve of the bias for different complexity of the model, right? And with that, we want to reduce the error as well. So I want you to pay attention that the focus of bagging and boosting is different. In bagging, we reduce the model variance. In boosting, the algorithm is trying to reduce the model bias, right? But overall, both of them are going to outperform decision trees by a large margin. Okay. Now let's talk about ensemble learning. So when we say ensemble learning, the idea is that why not use predictions of a group or ensemble of models, right? Ensemble learning means that we are combining the predictions from a collection of models, right? And as we discussed it earlier, the idea of trying to learn, the idea is that instead of trying to learn one super accurate model, let's focus on training many low accuracy models and then combine the predictions given by those weak models, right? So we know that, for example, in random forest and bagging, we know that we can start with a simple decision tree, right? This simple decision tree, we call it the weak learner because we know that the accuracy is not that high. So the idea is that let's resample from the data and make lots of trees out of this one simple data set, right? So we come up with different predictions, and then let's combine all these predictions together. So this is the idea, and call it strong learner, right? And it happens because of the statistical property. When you look at the variance of the let's say combined estimator, the variance is going to be smaller, right? And for example, the variance of the sample average is, so we all know that the variance of x bar, if x bar is the sample average, is going to depends on sigma divided by n, right? As the number of samples increase, as the number of observations in the sample increase, the variance of x is going to decrease, x bar is going to decrease, right? The same story is true here for our machine learning algorithm. So in machine learning algorithm, we are focusing on the variance of f hat of x, right? At the end of the day, we want to estimate this this functional form, this f hat of x, right? And then we know that it's going to be a combination of bunch of f hat. Let's say this is tree number 1 plus f hat tree number 2 plus f hat tree number 3, and etc. Right? And we know that we have b, well, let's say we have capital B of these trees, right? So the variance is going to be the variance of tree number 1 plus variance of tree number 2 plus the covariance between the trees, right? The covariance between, let's say, tree 1 and tree 2, and etc. And in the denominator, we have capital letter B, right? So we see that the variance of the ensemble methods depends on the variance of the individual methods. and the covariance between them, right? So this is key, right? And the idea is that can be reduced individual variances by a lot, and then when you divide it by b, the overall variance of the ensemble method is going to be smaller than the variance of the single tree. Okay, so that's the big picture. Okay, and so ensemble learnings typically produce more accurate and more stable predictions than the best single model, right? And ensemble learning methods are based on in general, based on two groups, right? Two methods. The first one is based on aggregation of the heterogeneous learners, and the second one is based on aggregation of homogeneous learners. So what do we mean by heterogeneous and homogeneous learners? So heterogeneous learners means that we're dealing with different models, right? So the models are different from each other. They're heterogeneous. So we can have SVM, we can have decision tree, we can have, I don't know, KNN, you name it, whatever model that we have covered so far in the class, right? Or any other machine learning models. So the idea is that let's work with the same data set, but apply different models and then aggregate the predictions. If it is classification, look at the majority class vote, right? If it is prediction, if it is regression, let's take the average. So that's the idea of heterogeneous learners. For homogeneous learners, however, the model is unique. We have one model, right? So let's say the weak learners are only decision trees, but we will work with different variations of the same data set, right? So we're going to resample from the data set thousands of times, and then we will end up with thousands of predictions for the data, right? And then we're going to aggregate over those predictions if it is classification or regression, right? So for the heterogeneous learners, we will end up with voting classifiers or average predictions. For homogeneous learners, we will do either bagging or boosting, right? Both of them have involved the idea of bootstrapping from the same data set thousands of times. Okay. And of course, we can have a combination of two, right? So let's say we have SVM, we have decision trees, we have random forest itself, we have KNN. So if I do something like this, so random forest itself is an aggregation of homogeneous learners, and these are heterogeneous ones. So it's a combination of them all, right? So this is called combined models. All right. Okay. Now that we know what is the definition of ensemble methods or ensemble learning, let's move on to the definition of bagging versus boosting in a more formal way. So bagging consists of creating many copies of the training data, and each copy is slightly different from the other one, right? So let's say this is my main training set, and I'm generating multiple copies, right? So copy number 1, copy number 2, copy number 3, right? And then I'll apply the weak learner to each copy to obtain multiple weak models and then combine them, right? So let's say I have a decision tree here, I have a decision tree here, I have a decision tree here, and then we'll combine them to get the final prediction. Again, if it is classification, majority votes. If it is regression, just simply take the average, right? So this is the definition of bagging. Again, consists of creating many copies of the training data. For boosting, however, the boosting consists of using the original training. So basically, we will work with our original data set and iteratively creating multiple models by using a weak learner, right? So the idea is boosting is very neat. So it says that, okay, take the original data and then apply a weak learner to that decision tree, let's say. Whatever is explained, let's pass it to the final output. Whatever is unexplained, or let's call it residuals, it will be passed to the second step, right? So the residuals are going to go down this path. And the second, so the idea is that this data is going to be the unexplained part of the original data set, right? We're going to use another weak learner on those errors, and we want to fix them. Whatever part is fixed, we pass it to the outputs. Whatever is not fixed, we pass it to the new data set. Again, the new data set is going to be the residual of the previous step, right? And then finally, we are going to repeat this process sequentially until there's a stopping criteria or we are satisfied with the outputs, right? And all of these things are going to contribute to the final output. The output is a prediction, right? So that's the idea of boosting. So boosting and bagging are different in this way. Okay, now let's talk about what's behind the scene for bagging and random forest in this class. And next class, we will cover the boosting. Okay, so bagging stands for bootstrap aggregation. Imagine this is our original training set, right? We have 4 features. So let's say the number of features is 4, and we're going to show the number of features with M. I'm sorry, with letter P. And let's say we have 5 observations. So N is 5, and our P is equal to 4. P is the number of features, right? Then we're going to bootstrap from this data. So what is the definition of bootstrap? Bootstrap means repeated sampling with replacement. So I'm drawing a sample from these 5 observations with replacement, and I do it thousands of times. So let's say the first bootstrap, so let's call it B1. This is the first bootstrap. Look at that. Observation number 1 shows up multiple times, number 3 multiple times, and number 4 once, right? So this is a subset of our the train set. And the reason that we see multiple of these things is because Bootstrap in general is sampling from the data set with replacements, right? So I can have multiple observation number 1, multiple observation number 3, and etc. Right? And then look at that. The important thing is that all the 4 features, yeah, I keep writing M. So all the 4 features are used in this random draw from the model, right? So bootstrap number 1, then bootstrap number 2, bootstrap number 3, and etc. And then finally, this is our last bootstrap. Let's call it bootstrap number capital letter B, right? And look at that in the bootstrap number 2, we have the observation number 2 has been repeated a couple of times, number 5 a couple of times, and then 3 once, right? Again, this is another draw from the data set. And finally, the same story for the last bootstrap. So this step is called bootstrapping, drawing from the data with replacement. So random draw from the data with replacement. Now, we look at each bootstrap data, and then we build the weak learner on that, right? So we are, for example, we're going to use a decision tree and apply it to the bootstrap number 1 data, and then come up with a prediction, right? So this is the prediction, let's call it F hat of bootstrap number 1. We do the same, we use the weak learners, and we do the same for all the bootstraps. So F hat B2, and etc. And then finally, this is our F hat B capital letter B. So this part, these are ensemble trees. And then we are aggregating, at the end of the day, we will aggregate the outputs by, if it is regression, we look at the average of these. If it is classification, we look at the majority vote. So that's the idea of bootstrap aggregation or bagging. So bootstrap aggregation is a general purpose procedure for reducing the variance of a learning method, right? Again, I said it earlier, but remember, the way that Bootstrap is able to reduce the variance is that we know that the variance of sum of estimated variables is the variance. Well, let me actually write it down again, because this becomes very important when we want to talk about the difference between bagging and random forest. So we have, this is, let's say this is the variance of F hat, our ensemble method. It's going to be equal to the variance of F hat 1 plus variance of F hat 2 plus, of course, it depends on the covariance of F hat 1 and 2 and every other pairs, right? So if I have thousands of these bootstrap, I will have thousands of these numbers. The entire thing divided by B. So this is a really important equation. So I want you to pay attention to how the bagging and boosting are able to, and the random forests are able to reduce the variance. So we say that the variance of the ensemble method is going to be a summation of the variances, and we know that the variances, the individual variances are going to decrease a lot. And also the covariance is going to be added, but the entire thing is going to be divided by B. So if we repeat this bootstrapping many more times, the variance is going to shrink even further. Okay, now we already covered this one. Given a training set, first we create B random samples. And then for each sample, a little small letter b, we build a decision tree. Again, this is our weak learner. We call it FB or F hat of B. It really doesn't matter. That's the estimated version. And after training, we have B decision trees. The predictions for a new data set observation X is obtained as average of B for regression or the majority of both for classification. And this is a formula for that, right? So it's very straightforward. Whatever those prediction numbers were out of each decision tree, we're going to take the average by dividing it by capital letter B to come up with the ensemble prediction. And if it is classification, what was the most frequent prediction? Bagging is a very useful technique because it helps to improve the stability of predictions and protect against overfitting. So what does that mean? Remember, if you reduce the variance, if we reduce the model variance, we are reducing the overfitting. Right? Because again, if the variance is small, it means that if you try the model in a new data set or in the different versions of the data set, it's not going to overfit necessarily. All right, so that was the idea of bagging. Now let's see what's the difference between bagging and random forest. So random forest is a subset of bagging, right? It's a special case of bagging. And we're going to see that the random forest provides an improvement over the vanilla bagging algorithm. So the vanilla bagging algorithm is the one that we just covered, right? And it's going to do that, random forest improve the performance of the bagging by doing a small trick, and that trick is decorrelating the trees, right? So why do we care about the decorrelation of the trees? Going back to the previous slide, look at that. If somehow I can reduce the covariance between these trees, the variance is going to, the ensemble variance is going to shrink even further. So that's the advantage of random forest over bagging. So we're going to use a trick, and that trick is going to enable us to reduce these covariance terms. And it's a good thing if you can reduce the covariance term, because it's going to reduce the our ensemble method variance more compared to bagging. Okay. Random forest uses a modified tree learning algorithm that at each split it inspects a random subset of the features. So it's not going to go over the entire feature set. It's going to look at the subset of those features, right? And this is going to do two things. First of all, it's going to increase the variation between the, when I say increase the variation, I mean increase the variation of different models that you're using, right? The model is a decision tree, but the data is different. We go over different features, and it's a good thing. And also is going to speed up the process, right? Because let's say we have thousands of features. So instead of working with thousands of features, each tree is going to work with a subset of those thousands. Let's say it's work with hundreds of them, not instead of thousands. Right? So in that sense, random forests are usually outperforming the bagging in general. The reason for doing this, by this I mean using a random subset of the features, is to avoid correlation of the trees, right? So we want to reduce the correlation of the trees. And think about it. This is a code from the Introduction to Statistical Learning in R. Our main textbook for the course, and it says that suppose there is one very strong feature in the data set. When using bag trees, most of the trees will use the same feature as a top split, right? And that results in an ensemble of similar trees that are highly correlated. So if I go back to the previous slide, look at this one. Do you agree that if we use all the features, P is equal to 4, P is equal to 4, P is equal to 4, right? If you use, we used to have 4 features, and if I use all the 4 features, and these trees are going to be very highly correlated with each other, right? So in order to avoid that, random forest is going to do a trick, and the difference between random forest and bagging is here. it's going to work with a subset of features at each split, right? So instead of working with feature 1, 2, 3, 4, here it's going to only work with 1 and 4. In this tree, only 2 and 3. This tree, only 1 and 3, right? The features. So work with a subset of trees. And by this way, it's going to decorrelate these trees. And we know that if we decorrelate the trees, it's going to reduce the model variance even further compared to bagging, right? And yeah, the rest of it is the same as bagging. You know, we have bootstrap, you know, random sampling from the data set with replacement. And then we come up with different weak learners. And finally, we aggregate, right? However, be very careful. You know, in random forest, the random subset of features happen at each split, right? So it's not like that we start with feature 1 and 4 and we use feature 1 and 4 for the entire decision tree, right? At the first split, we look at 1 and 4. At the second split, maybe we look at 1 and 3. At again, as we go over each split, well, this is a terminal one. So if we go over each split, a subset of features is going to be candidates, right? So this way, it is guaranteed that all the features from the model has a chance to show up in the algorithm, right? So even if at the first split you think that the model is missing one of the most important features, then you shouldn't be worried about it because those features have enough chance to show up in the algorithm down the road. Okay. Now let's talk about, let's compare the performance of the random forest and bagging. So this subset of features, we're going to use letter M. So for example, M here is 2, right? Subset of features. Instead of 4 features, we're going to work with 2 features. Remember, our number of features was 4 in the original train set, and then M can be equal to 2 and can be any number less than 4, right? So now you can agree that if M is exactly equal to P, our random forest is going to be our simple bagging. So that's why I said that random forest is a subset of bagging, right? But in practice, usually we use the M to be very smaller than, than the P, right? So for example, we use P over 2, we use the square root of P. We use log to the base of 2 of P, right? And if I want to give you an example, imagine, let's say the original data has 10,000 features, right? So then random forest, instead of using 10,000 features, is going to, in this case, is going to only use 100 of them. You can see that how faster random forest can do the job, right? Because at each split, instead of going over 10,000 features, it's going to inspect only 100 features. So it's going to be a lot faster than decision trees for huge data sets, right? So this is another advantage of random forest against bagging. But here, let's look at the performance of the random forest versus bagging. Imagine we're talking about a classification model, and on the vertical axis we have test classification error. On the horizontal we have model complexity, right, or the number of trees. If M is equal to P, this is our bagging model. If M is equal to P or anything less than P, this is our random forest, right? So it seems that, so let's look at, so for example, around here. So it seems that at this point, at this complexity of the level of complexity, the bagging is out, well, yeah, the random forest when M is equal to the square root of P is outperforming the random forest when M is equal to P over 2, and it's outperforming our bagging, right? Because remember, these are classification errors. The model with the smaller classification error is a better one, right? So as you can see, at some point, it seems that always the random forest model, let's call it random forest model number 1, is outperforming the bagging, and bagging is outperforming the random forest model number 2, right? So again, depending on how we pick M, the random forest can outperform bagging or not, right? At least in this example. So this is going to be one of the hyperparameters that we need to tune when dealing with random forest models. Okay, now let's go to the next part, which is hyperparameters and feature importance. So the most important hyperparameters for random forest are the following, right? So most of them are, there's an overlap between these hyperparameters and the decision trees, right? Because Random forests are derived from decision trees. It's a tree-based model. But the new ones that we didn't see them in the decision trees are M and B. As you saw from previous slide, it makes a big deal how big change in the performance of the model how we use M, right? So the number of subset features, so this is one of the hyperparameters. Then the number of trees themselves, this is capital letter B. And in Python, it's called number of estimators. Remember, each of those decision trees is going to work as an estimator, right? As a weak learner. So we can say, okay, I want to work with 100 of those weak learners, or 500 of those weak learners, or 1,000 of those weak learners. Remember, the larger this number it is, the smaller the model variance. But there's some optimal level, right? By optimal, I mean that it's not worth to increase the computational cost by adding thousands of more trees if the variance model, overall variance model, is going to reduce only by a tiny little bit, right? Then the rest of them, we have seen these things before. The minimum size of each node or each terminal node, the maximum number of leaf nodes, the maximum number of terminal nodes. So how many terminal nodes we want to see, the maximum depth of the tree, and remember depth was the longest path from the root node to the terminal node. And finally, we can play around with the criteria itself. So if it is classification, we will use either Gini or entropy. If it is regression, there's no choice. We can always use RSS, right? Mean squared error or RSS. Then we can use grid search cross-validation. This, we have seen this before in our SVM algorithm. So we can use grid search cross-validation to tune the hyperparameters and pick up the best model. So the good thing about grid search is that we can get a better model by starting from some random values for the features. But the bad news is that it can be, we can end up in a local optimal, right? So because it's difficult to sometimes it's you do grid search cross-validation and you'll see that your model is not outperforming as you expect compared to the vanilla version of the model with the default inputs. Okay, now let's talk about feature importance. So what is feature importance? So we know that random forest is relatively black box, and the reason that we say it's relatively black box because yes, we cannot interpret the model in general because basically we cannot track of all those thousands of bootstrap trees down the road. But this doesn't mean that it's going to be entirely black box. So we can still rank the features, and this is a very powerful property of random forest in general. And decision trees, actually. It's not only for random forest. For simple decision tree, we can use feature importance as well. So let's look at an example. Imagine we are using the Logan housing data set. So this is a housing data set, and these are the features. So total square feet, garage capacity, total bathroom, total bedroom, year built, HOA, days on the market, sold terms, month sold, and etc. Right? At the end of the day, we can rank these features using random forest. What is it? So, for example, in this case, in this example that we're looking at, in this example, it seems that total square feet is the most important feature among all the features. And then the next one is garage capacity and etc. And the least important feature in the model was irregular shape. So if a property has an irregular shape, I assume it's interior. By irregular, sure, it doesn't mean outside, it means inside, interior design. And it has the least important effect on the model, right? That makes pretty much sense. Now let's see how random forest is able to rank these features. Okay, so feature importance refers to a technique that assigns a score to input features based on how useful they are. So let's see what do we mean by score and how useful they are. So a score, if it is regression, the score is basically our RSS. If it is classification, we can look at Gini or entropy, right? Impurity index. Then by useful, so for regression, we look at each feature, and we see each feature is reducing, for example, in regression, is reducing the RSS by how much, or each feature is reducing the Gini and entropy by how much, right? So this is what we mean by useful. So for random forest, the total amount that the RSS is decreased, or the Gini index or entropy is decreased, due to a split over a given predictor, average overall B trees. So this is basically that score that we're talking to. A large number indicates important predictor, because a large number means a larger reduction in the RSS, a larger reduction in the impurity, right? And so if you want to think of an example, so imagine we have thousands of trees, and this total square feet is going to show up thousands of times among those for each split among those trees. And then at each split, we're going to record, for example, how much this Gini or RSS reduced. And then we're going to add up all those numbers for the entire model and then report that number, right? So this number, for example, it's 0.35. And this number is going to change based on the units of the variables, of the target variable, and if it is classification versus regression. So basically, we cannot interpret this number in terms of magnitude. So but we can simply rank the features, right? So we can say that, okay, total square feet is more important than the zip code, than the years sold, and etc. But we cannot say anything about this quantity itself. It's not interpretable. Okay, now finally, last part, let's talk about pros and cons and then applications in finance. So let's start with the pros. One of the most, so we know that random forest is one of the most widely used ensemble learning algorithm. The reason is that on top of all the advantages that we saw last class for decision trees, it can do the followings. And remember, as a reminder, what were the advantages of decision trees? We said that decision trees can handle categorical data without the use of making them dummy variables. And this helps us a lot in terms of reducing the dimensionality, right? And decision trees can learn nonlinear patterns very effectively by, we know that in a decision tree, each, let's say, imagine, for example, you're looking at the default, this is FICO score. Each variable, each feature can show up multiple times down the tree, right? So FICO here then we have FICO, let's say FICO here. So this is going to capture some nonlinear pattern. So this is decision trees are going to be able to easily capture that nonlinear pattern. And the final one was, we didn't need to do any processing, pre-processing the data for decision trees, right? And this was also huge. So we don't need to be worried about, okay, standardization or normalization, which one should we use, min max normalization, and etc. And then decision trees are non-parametric, so it means that they can be super flexible, right? So they can capture more nonlinear patterns easier compared to other models that we are imposing some functional forms, or we are imposing some distribution for the data. So random forest, on top of all these good advantages of decision trees, can do this thing, can avoid overfitting by reducing the model variance. So this is a big deal, right? And one of the caveats of decision trees was that if you didn't prune them back, they would overfit, and the accuracy of the model was poor in the test set. This random forest can avoid that. Random forests are parallelizable. So what does it mean? It means that if you're working with terabytes of data, or data set with millions of records, so we can split them. And so imagine this is your data set. You can split them to multiple sections and then apply a random forest to each. So imagine, I don't know, you have an 8-core CPU. Each core is using one of them, and then we can aggregate over all the predictions at the end of the day. So it's going to be faster when it comes to working with larger data sets. It is great with high dimensionality. Why? Because we said that we don't, well, first of all, it's going to reduce the dimensionality by we don't need to make dummy variables make categorical variables into dummies necessarily. So this is a huge advantage. And random forest in general can handle high dimensional data easily. And finally, quick training and prediction speed, right? Why? Again, because it's going to reduce the dimension of the data. By reducing, I don't mean that it's, for example, it's going to make it from 100 to 50. I said when compared to auto models, and then we have lots of categorical variables, right? So random forests are going to they work with a subset of features instead of the entire feature, so it's going to be faster. So, are there any disadvantages to random forests? Yes, and we can somehow I don't know, deal with them. So maybe the most important disadvantage of the random forest is that it's not interpretable, right? It lacks the ease of interpretability of the simple decision trees, and it's relatively black box. Why relatively? Because again, we have the feature importance. We can rank the features, but we cannot say anything about the causality, the significance, the magnitude of the effect, and things like that. And finally, it can overfit without tuning the hyperparameters. So it says basically, as you pay attention, overfit can show in both advantage and disadvantage. We said that, okay, it can avoid overfit, but in a disadvantage, you say it can overfit. It can overfit only if you're not tuning hyperparameters. Okay. All right, now let's talk about the applications in finance. And there are lots of applications when it comes to using random forest in finance. And here's just a list of a bunch of them. In factor-based investment strategies for asset allocation and investment selection, we can use random forest. Remember, in decision trees, we said we can use decision trees to come up with asset allocation. For example, what percentage should goes to equity, what percentage goes to fixed income, and then among those equity and fixed income, for example, what sector of the equity, what duration of the fixed income, and things like that. In random forest, we can do the same by looking at the feature importance, right? We can rank the feature importance and then weight the asset allocation based on the ranks of the feature importance. So this is something that we can do. And we can also do the same for investment selection. Then another example is predicting whether an IPO will be successful or not based on some ranked factors, right? So what are the ranked factors? For example, we want to look at the previous IPOs and basically see what was the percentage of oversubscribed. We will say an initial public offering when is oversubscribed when the number of shares that the investors are requesting more than the shares are offered. So this is oversubscribed. So if the percent oversubscribed is higher, it means that the IPO is more attractive, right? Then we can look at the first trading close price. We can look at the first trading volume. These are all features. At the end of the day, random forest can rank them, and then you can make predictions for a new IPO, and then see if it is a good investment or not, right? Again, these examples, there are lots of other examples that we can think of, but these are some of the examples in finance. And then finally, we can use random forest for fundamental factor modeling, right? So we know that out there is a zoo of factors. We're talking about hundreds of thousands of factors out there in finance literature. And when it comes to asset pricing, we don't know which one to use, right? Or at least even among those that the analyst has, they agree on. Let's say, for example, we're doing uh, stock valuation using some comparables, right? For example, we look at companies' PE, EV/EBITDA, price over sale, price over book ratio, and then it is we know that it's well known that many analysts use PE ratio to evaluate a stock. But why PE? Why not PO, price over sale? Why not price over booking? And if a combination of them, what percentage, right? So how should do we weight these factors? So we can use random forest, and then we can look at the feature importance and then use the weights of the feature importance as a weight for these inputs for the asset pricing. However, when it comes to factor modeling like this using random forest, we know that we're dealing with time series random forest, and it's a little more subtle than our simple random forest. So for example, we cannot do bootstrap, we cannot use our simple cross validation. We have to make sure that if you're doing bootstrap, we have to use sequential bootstrap or stationary bootstrap. if you're doing cross-validation, we have to apply the cross-validation based on, we have to apply time series cross-validation. So it's going to be a little different, but I just wanted to let you know that if you want to apply random forest, do not apply it blindly to time series data, because there are very, very subtle things when it comes to time series, and you should not just blindly apply any machine learning models to time series. Just pay attention to that. Okay, and finally, let's see what is the question of the day. So the question of the day for you is that, is this a, so let's see, what's the story of that? So we have, you're seeing an elephant here, right? And there are different people looking at different part of this elephant and then make a prediction. So for example, this guy is looking at is just touching the ears and says, okay, it's a fan. This guy is just touching to the elephant's body. It's a wall. This guy is just holding the tail and say, okay, it's a rope, right? And as you can see, each of these people are making a different prediction, right? Of course, they have closed their eyes, so they're making the predictions by just getting some inputs, right? So this one says it's a tree, it's a snake, it's a spear, because she's touching this, right? So, and the question is that, is this bagging or random forest? What do you think? Okay, I hope that you made a guess. And this is going to be random forest, because look at that. We have weak learners. We have multiple weak learners that are working with a subset of features, right? So what are the features? Let's say we have ears, we have this one too, we have body, we have, I don't know, tail, 5, 6. Let's say we have 6 features, right? And each of these weak learners are working with a subset of features, right? And then making a prediction. So this is going to be random forest because we're using the subset of features. And again, this is a very exaggerated example. So we know that in general, we can work with a subset of these features, and these features, and make a prediction. And eventually, if you put together all these predictions, hopefully the answer is elephants, right? The idea is that why not leverage the wisdom of the crowds when you're making predictions? All right, so that was it. That was the theory of random forest. In our next class, and bagging, in our next class, we will be covering the random forest and bagging in Python. Until then, have a good one.